Now we're going to go over rational functions, their graphs, how we use them, and some real life situations. Now a rational function is pretty much when you're dividing two functions together. And you're dividing, say, one function q of x to another function p of x. They're both polynomials and the denominator can never be 0. The first type of rational function we're going to look at is what we call the reciprocal function. That's when you have some number divided by a linear term x. And it's always undefined at whatever term would make the denominator equal to 0. So the domain, notice it's all the x values besides 0. We have parentheses to show that 0 is not in our domain. And it's all other x values. Likewise, the range. You notice there's a horizontal asymptote at through the x-axis, or where y is equal to 0. So the range would be all other y values besides 0. So that's why there are parentheses around 0, and we just do the union. Now, since it's just positive 1 over x, if you notice it's constantly decreasing as the x value increases. For this branch here, the y values are decreasing. Likewise, for this branch, the y values are still decreasing. And since it's discontinuous at x equals 0, again, that's why it's not in the domain. And this is what we call an odd function. An odd function means that if you were to plug negative x into our function, you'd get the same thing out. Or you'd actually get the opposite thing out. So if you plug in negative x, you will get negative f of x. So for example 1, it says graph this function. Now, you notice the only things that change is that the numerator is now 2 instead of 1, and there's a negative sign in front. The negative sign means that instead of the graph looking like this, it's now going to look like the red function. The graph's going to look something like that. Since we haven't shifted it left or right any, the asymptotes are still going to be at the axes x and y. It just means that the 2 just means it's going to be stretched out a little bit more. It's going to increase at a faster rate. So here's a nice picture of what the graph should look like. So if you look, it does follow the same general shape as the red graph. It's just that, you notice as the x values increase, the y values are constantly increasing for this branch, and then on the other side of the vertical axis as well. The y values are still increasing. So it's increasing on the same range from negative infinity to 0, union with the interval from 0 to infinity. And the domain would be the same interval in which it's increasing from negative infinity to 0, unioned with the interval from 0 to infinity. Now we're told to graph this. This would also be a rational function because it's just, there's no x squared or x to the third term on the bottom. The highest x term is just x. So to figure out the domain, you take the denominator, set it equal to 0. That could have worked on the first example too. Just at the first example, had you set the denominator equal to 0, you would have already found your x. The x, for this example, the x value that makes the denominator equal to 0 is negative 1. So the domain would be all the x values from negative infinity to negative 1, union with all the values greater than negative 1. And if you notice, since there's no negative sign in front, that means the graph will look something like this if we plot our vertical asymptote. The graph will look something like this. And if you notice, as the x values are increasing, the y values are still decreasing, so it's decreasing on the domain from negative infinity to negative 1 union with the interval from negative 1 to infinity. And the range. You notice the range, since it hasn't been shifted up or down, the range would still be the same as in the previous example from negative infinity to 0, unioned with the interval from 0 to infinity. The way we could tell that it was shifted up or down is, see on the end, it would have given us we would have been adding or subtracting some number, we could call it C. If we were adding a number, it would have been shifted, the horizontal asymptote would have been shifted upward. If it was minus some number C, it would be shifted downward on the end. The next type of rational function we're going to talk about is the 1 over x squared. The domain, now for this function, if you plug in 0 into the denominator, you'd still get 0 for the denominators, which would make it undefined. So the domain would still be all x values except for 0. But if you notice, it never goes below 0. That's because the squared term makes any other x value positive. So that's why all the y values are non-negative, and it never goes below the horizontal asymptote. Now, it says it's increasing on the left branch as you go from left to right, and as you go from 0 to the right, the y values get smaller, so it's decreasing on the positive x values. Now, say if it were negative 1 over x squared, the graph would look like this, below the x-axis. It would look like the purple graph, kind of. It would just be flipped across. Now, you're told to graph this function y equals 1 over x plus 2 squared minus 1. And get the domain and range. So, you notice the denominator says x plus 2 squared. The denominator is only equal to 0 where x plus 2 is equal to 0. So if you solve that for x, you'll find there's a vertical asymptote at negative 2. So we drew our vertical asymptote here at where x is negative 2. And since we have minus 1 on the end, that means the horizontal asymptote is shifted down 1 unit. So there's a horizontal asymptote where the y value is negative 1. And since there's no negative sign in front, that means both branches are above the horizontal asymptote, so it'd look like the black graph. And the range, since the domain was all the x values besides negative 2, the range would be all the y values except for the horizontal asymptote, which would be negative 1. So it'd be negative infinity to negative 1, unioned with the values from negative 1 to positive infinity. Alright, now let's talk about how to determine the asymptotes of a rational function. If we're talking about vertical asymptotes, just find where the denominator is equal to 0. Find the x values that make the denominator equal to 0. Those would be where your vertical asymptotes are located. Now, any other asymptotes, whether it be horizontal or slanted, we'll talk about slanted in part C, but there are 2 ways to determine a vertical asymptote. If the numerator has a lesser degree than the denominator, then there's a horizontal asymptote at the x-axis. Like say, if you end up with a rational function like 2x squared over 3x to the 9th. Since the degree of the denominator is greater than the degree of the numerator, then there's a horizontal asymptote at the x-axis at y equals 0. And if they have the same degree, part B, Like say if they have 2x to the fourth divided by 5x to the fourth, then that means there's a horizontal asymptote. You can find the horizontal asymptote by dividing the leading coefficients, 2 and 5. And if the numerator is exactly 1 degree more than the denominator, like say if you have 2x to the third minus x plus 6 all over 3x squared minus 4, then you can divide the numerator by the denominator and then ignore the remainder. Alright, here's a 3-part example. It says for each rational function, find all the asymptotes. So for part A, for the vertical asymptotes, that would be where the denominator is equal to 0, which means it'd be where 2x minus 1 is equal to 0 and where x plus 3 is equal to 0. Now where 2x minus 1 is equal to 0, if you add 1, you have 2x is equal to 1, then divide by 2. You get a vertical asymptote at 1/2. And if you subtract 3 from both sides on this factor, you get that there's a vertical asymptote at x equals -3. So that's where the vertical asymptotes are located. And to check for any other asymptotes, say horizontal. You notice the degree for the numerator is 1. And if you were to FOIL these, you would have 2x squared plus 5x minus 3, which means the degree of the denominator is 2. Since the degree of the denominator is greater than the degree of the numerator, there's a horizontal asymptote at 0. Part B, it says y equals 2x plus 1 over x minus 3. Now for the vertical asymptote, there's only one factor on the denominator, and that's x minus 3. So set that equal to 0 and solve for it by adding 3. You get there's a vertical asymptote at positive 3. You notice there, to figure out the horizontal asymptote, if you notice the degree for both the numerator and the denominator is 1. So you can divide the leading coefficients. The coefficient of the numerator is 2. The leading coefficient of the denominator is 1. So divide it 2 over 1, which tells you there's a horizontal asymptote at y equals 2. Now for part C, it says y equals x squared plus 1 over x minus 2. To find the vertical asymptotes, you set the denominator equal to 0, then solve for x. That tells you for this example there's a vertical asymptote at x equals 2. Now if you notice for the other types of asymptotes, the degree for the numerator is 2, the degree for the denominator is 1. Since the degree of the numerator is 1 more than the degree of the denominator, we have a slanted asymptote. So, we can use synthetic division. If x minus 2 is what we're dividing by, then that means we'd use positive 2 for synthetic division. And then we write the coefficients. The coefficient of x squared is 1. Since there's no x term, that's like having a coefficient of 0. And then the constant is 1. So bring down the leading coefficient. 1 times 2 is 2. 0 plus 2 is 2. 2 times 2 is 4. 1 plus 4 is 5. Now we were told to ignore the remainder. So that means there's a slanted asymptote at y equals 1x, or just x, plus 2. That means as the y values get higher up, really high or really low, they'll follow the same line, y equals positive x plus 2. Now we're going to go over how to graph a rational function. Alright, pretty much steps 1 and 2 say you start off by finding all the asymptotes horizontal, vertical, and oblique or slanted. You also should find the y-intercept. Find the x-intercept by solving where the function is equal to 0. What step 4 means is the x-intercepts are located where the numerator is equal to 0. Determine whether it crosses its non-vertical asymptote by setting the function equal to b, or the non-vertical asymptote, the slanted one. Plot any necessary points and then complete the sketch by connecting the dots. I have some examples of what this would look like. Now we need to find the x-intercept, where it crosses the x-axis. Remember, the x-intercept is found by taking the numerator and set it equal to 0, and then solve for x. So that tells you that x is equal to -1, so it crosses the x-axis at the point -1, 0. Now part 5 says determine if it crosses its non-vertical asymptote. Since its non-vertical asymptote, which is the horizontal asymptote, is just the x-axis, we know it crosses the horizontal asymptote at -1, 0. Alright, now we need to determine on what intervals is the graph positive or negative, meaning whether it's above the y-axis or below. So remember the horizontal asymptotes were at, I believe, 1/2 and -3. There's also the x-intercept at -1, so we have 4 different intervals we need to test. If we pick any x value less than -3, say -4, plug that in to our interval. Say -4, remember our function is x plus 1 over 2x minus 1 times x plus 3. If we plug in -4, we have -4 plus 1, which is -3, so you have a negative number on top. Plug in -4 into the denominator. You have 2 times -4, which is -8, minus 1 is -9, so you have a negative number times -4 plus 8 is -1, so it's multiplied by a negative. So you end up with a negative over a positive, which means to the left of -3, it's negative, which means it's below the x-axis. From -3 to +1, so pick any number, say -2. You still have a negative number on top. Then 2 times -2 minus 1 gives you a negative. Then -2 plus 3 is +1, which means it gives you a positive, so you end up with a negative over a negative, which means is positive on this interval, meaning from -3 to the x-axis, or not to the x-axis, to the x-intercept, from the asymptote -3 to the x-intercept -1, it's above the x-axis. And from -1 to +1/2, pick any number between -1 and +1/2, say 0. 0 plus 1 is 1, so it means you'd have a positive number on top, on the numerator. If you plug in 0, you'd have negative, because 2 times 0 is 0, minus 1 is -1, and then 0 plus 3 is positive 3, so it's positive. So you end up with a positive over a negative, which means it's below the x-axis from -1 to 1/2. And then pick any number greater than 1/2, say 1. 1 plus 1 is 2, so it's positive on the numerator. And plug in 1 into the denominator, you have 2 times 1 is 2, minus 1, so it's positive. Plug in 1 into x plus 3, you still end up with positive, which means it's above the x-axis for all values greater than 1/2. So, if you want to plot those points, or keep in mind those intervals, that means the graph will look something like this. If this is the interval, remember that would be a vertical asymptote. Since it's positive here and negative here, the graph would go like that in that interval between the asymptotes. And since it's positive to the right of 1/2, that means the graph should look something like that. And you know the branch is this way because since the horizontal asymptote is 0, that means as x gets greater, the branch gets closer to the horizontal asymptote. And here's a nice picture of what the graph should look like. Notice it looks pretty similar to the purple graph we drew. We're going to skip a few examples out of the book and we're going to skip to example 9 out of the book. Graph this function. Now it's possible that you could possibly factor it down and cancel stuff out. Like for this function, x squared minus 4 is a difference of squares. So you could factor that down to square root of x squared is x, square root of 4 is 2. And since it's a difference of squares, one would be plus, one would be minus. And bring down the x minus 2 on the bottom. Now if you notice, this graph of this function would look the same as just the linear function x plus 2. It's just that whenever you plug in 2, because remember x minus 2, set that equal to 0 and solve. That means the value of x equals positive 2 is not in the domain. So that means if you plug in 2 into this function here, the point 2, 4 is not on your graph. So if you were to graph this function, graph this function x squared minus 4 over x minus 2 would look the same as x plus 2, so start at your y-intercept of 2. So there would be an open circle at the point 2, 4. But you'd otherwise keep drawing it.